Hi everyone, welcome to my videos on elementary differential equations. This is video number 2 for chapter 7 and the topic is on systems of two nonlinear differential equations. In this video, we consider applications of autonomous systems in the population dynamics. So in particular, we'll go through two models and the meaning of the models, and we will find critical points for these systems. Our first example is about competing species. So now we have a habitat which is shared by two competing species, and now let x and y be the densities of these two species, and they are sharing the same natural resources. So another way of saying sharing is that they are competing for the same natural resources. So what is important here is that they are not in a prey-predator situation. So they will not terminate each other, but they will just be fighting for the same resource. Okay, so here is the model. So x prime will equal to x times a factor here is a constant m minus ax minus by. And for the y, it's kind of symmetric in a similar way with different coefficients. Y prime is y times a factor that is a constant n minus cx minus dy. So here we have a bunch of coefficients which are positive constants. These are the a and the b and c and d and the capital M and the capital N. And these terms, they have physical meanings. Okay, now let's take a look at the physical meaning of this system, which is in blue here. Let's consider the situation that species X lives alone. That is, the population for Y is 0. Then we just have the first equation. And where Y is 0, then we have X prime equals X times M minus AX, because BY is gone, Y is 0. So we recognize this as the logistic equation. So here the growth rate is the term m minus ax, and we also see that when this term is 0, that is when x equals m over a, then the rate x prime will be 0 and the population will stop growing there. So therefore the number capital M over a will be the maximum population density of species X that the habitat could support in absence of Y, where there is no Y. If we now introduce a second species into the habitat, we add Y into it, how would the existence of Y affect the growth of the X? Well, naturally, the rate of growth would decrease if Y is existing. Okay, and how strongly it affects the X population will be represented by this constant B. So we have this negative by term in the equation for X prime. Okay, and it's not difficult to understand now that a completely similar argument could be made for the case where y exists alone, that x is 0. Okay, so if x is 0, then we have y prime is y times n minus dy, again the logistic equation, and when y equal to n over d, this factor will be 0 and the population will stop growing. Therefore, this term here measures the max density of y the habitat could support when x does not exist. Now we search for critical points for the system here. So we had plenty of practice in the previous video, so we know we have an algorithm. These two equations on the right hand side, they're both factorized, so it's easy to conclude. So we want the first equation to be 0, which results in two possibilities, x equals 0, or the second factor is 0. And the same for the second equation, either y is 0 or the second factor is 0. And then the relation between these is an AND relation. So there are two possibilities here, and there are two possibilities here. And in theory, there can be 4 combinations. Okay, so now let's investigate these 4 combinations. Okay, the first combination, taking x equals 0 and y equals 0, and we see that the origin is a critical point, and that means it's an equilibrium. That means if initially there is no x or no y, none of the two species were ever present in the habitat, then they will never be anything. Okay, the second combination will be taking x equals 0 and take the second one here, that guy. And we see that when x is 0, this term is gone and y would be n over y. And then that is the second equilibrium. So what is the physical meaning of this equilibrium? Well, it is x equals 0, so the species for x doesn't exist, so y lives alone, and y has reached the maximum capacity of the habitat, so it doesn't change anymore. Now the third combination will take this one, which we list here, and then the first one here, y equals 0. So we can put y equals 0 and solve for x, which will be m over a. So we'll have m over a 0 as the third critical point. So this is the point where in the habitat the species y does not exist, so x lives alone and it has reached the maximum capacity and it doesn't grow anymore. And then there is the last one, and that is we take this condition and we take this condition. So we have two linear equations for the unknowns x and y. Okay, so here we need to solve a system of two linear equations, and the solution will very much depend on all the coefficients. It's a much more complicated situation. It might have a solution in the first quadrant and it might not, and there are different ways this can happen. So this is a much complicated situation. I will make an additional video on this topic, which will be coming soon. Our next model in population dynamic is the famous prey-predator model of Lotka-Volterra. So we're in a situation that we have a prey and a predator living in the habitat. And let now x be the population density of a prey. And for the predator, we let y denote the population density. So the assumption of the model is the prey and the predator, they are living in the same habitat. And in particular, the predator lives on eating the prey. And here the prey lives on natural resource, which we assume is abundant, which means the prey can keep growing without exhausting the natural resource. Okay, so let's present the model. It's the following. X prime is x times a minus by, and y prime is y times negative c plus dx. Here, the coefficients A, B, C, D are constants. They are actually all positive constants, and therefore we put negative signs clearly to indicate the effect. Okay, so now let's take a look at some physical explanation for this model. Let's consider the case where there's no predator, so y equals 0. So if y initially is 0, y will be 0 forever. Therefore, we just have x. So x prime will equal to a times x here. So we see that we have an exponential growth, and the rate for the growth is a. So this means when there is no predator, the prey will just grow exponentially with rate a. Such a growth is possible because of our assumption that the natural resource is abundant. Now, if the predator shall be present, the existence of the predator, we know by the model it should have a negative effect on the prey because the predator would eat the prey. Okay? And so we see the presence of this term, negative by, which is negative. On the other hand, if there is no prey, that is x is 0, then x is forever 0. And then y prime will just be, this term is gone, which we negative cy here. And we recognize this equation is an exponential decay with rate c. So the physical meaning of that will be if there's no prey, then the predator will have no food and it will die out. And then if the prey shall exist, it should be good news for the predator and it will feed the predator, so therefore it will have a positive effect on the growth rate. Therefore it's represented here with a plus dx term. Okay, now let's take a look at critical points, also the equilibriums. So the right-hand side is factorized, so we can easily write out. It will be x equals 0, or this one equals 0, which is y will equal to a over b. And for the second equation, y equals 0, or this term equals 0. That means x is c over d. So theoretically, there are 4 combinations. Let's look at it. We see that 2 of them are actually, 2 of the combinations will not give any solution. That is, if we combine this one from the first and this one from the second, and then c over d does not equal 0, so there's no solution. And then another combination is when y is 0, and then we pick this one, y is a over b. Again, that's a positive number, so there's no solution. So there are only 2 out of the 4 combinations that will give solution, which is take this one, combine with that, so 0, 0, the origin. And the second one is taking this condition with that one. So x is c over d, y is a over b. So that is the second critical point. Okay, so that's the end of this video, and what will come next will be an analysis of these critical points to see their stability and local behavior around the critical points, and hopefully using that information to understand how the solution of the system can be constructed. Okay, so that's all, and I hope you enjoyed this. See you next time.